It's now Thursday, November 25, 1915. Einstein is lecturing at the Prussian Academy for the fourth time in as many weeks.
With this, we have finally completed the general theory of relativity.
Einstein has the equations. The left-hand side is geometry. It describes warps and curves in the fabric of space and time. The right-hand side keeps track of the matter and energy within and moving through a region of space and time. And the equality, what we now call the Einstein field equations. This provides the choreography for the entwined cosmic dance of space and time, matter and energy. And remarkably, the equations tell a story that's a little different from the imagery I've been using, the imagery used in just about every popular account, which focuses upon the curvature of space. Because the math shows that time curves too, time warps, which means that clocks that are ever deeper in a gravitational field, they tick off time ever more slowly. In fact, in ordinary situations like tossing a cup, it is the warping of time that has the greatest impact on the resulting motion. And yet, for a body like the Earth, the size of that time warp, it's tiny. I mean, your heads are all generally a little higher up in Earth's gravitational field compared to your feet, which means your heads age a little more quickly than your feet, over the course of an average lifetime by about 100 billionths of a second. And yet, according to general relativity, that tiny time warp, that's why things fall. That's why you're anchored to your seats. Objects do not want to age. The math shows that things are drawn toward locations where time elapses more slowly. Who would have thought that the seemingly basic question asked by Isaac Newton 240 years earlier, how does gravity work, would result in such a dramatic upheaval in our understanding of reality?
I am quite overworked from the extraordinary exertions of the last few months, but the success is glorious.
One can barely imagine the elation of that glorious success. But Einstein is also now deeply concerned. He learns that Hilbert submitted his paper 5 days before him. And indeed, in the decades since, the priority for the discovery of general relativity has been debated. I mean, in that final chaotic week, did Einstein come up with the final form of the equations on his own, or did a little glance at Hilbert's paper show him the way? Did Hilbert's paper actually have the final form of the equations, or did Hilbert modify his paper prior to publication based on Einstein's insights? Part of the resolution has been lost to history, as a key section of the page proofs of Hilbert's paper have been snipped away, literally snipped away. By design, by chance, no one knows. But in the published version of his paper, Hilbert did not challenge Einstein for the discovery of the general theory of relativity.
The differential equations of gravitation that result are, as it seems to me, in agreement with the magnificent theory of general relativity established by Einstein.
There has been a certain ill feeling between us, the cause of which I do not wish to analyze. I have struggled against the feeling of bitterness attached to it with complete success. I think of you again with an unmixed geniality and ask you to try to do the same with me. It is a shame when two real fellows who have extricated themselves somewhat from this shabby world do not afford each other personal pleasure.
The road to the general theory of relativity was long. It was windy, bumpy, anxiety-provoking. The final result, a jewel. The theory was now done, but Einstein realized that there was still one remaining question. Is the general theory of relativity right? His use of the equations to explain Mercury's orbit was impressive, but a truly convincing test would require the theory to make a prediction about something not yet observed that scientists could go out and measure. Einstein knew just what to do. Since his earliest work toward the general theory of relativity, Einstein knew that in a gravitational field, light falls. Light travels along curved trajectories. And now, with the final form of the equations in hand, he could calculate the precise shape of those curved trajectories. So Einstein proposes testing those predictions through astronomical observations. Here's how. Light from a distant star travels along a nice straight trajectory when the Earth is on this side of the sun. But 6 months later, when the Earth is on the other side, that starlight needs to go through the warped region near the sun, which from Earth makes the position of the star in the sky appear to shift. Using the math of general relativity, Einstein was able to calculate the angle between those two locations. And it comes out to be 1.75 arc seconds. That's roughly the same as the angle between the bottom and the top edge of a dime viewed from 2 miles away. Tiny, but measurable. But doing so would require seeing distant stars during the day while the sun is out. I mean, how do you do that? Well, during a solar eclipse, the moon blocks out the sun's light, making the distant stars visible. So to test Einstein's prediction, astronomers would need to take photographic plates during a solar eclipse and compare them with photographs taken 6 months earlier. The British Astronomer Royal, Sir Frank Dyson, immediately set plans in motion to test this prediction during the upcoming solar eclipse of May 29, 1919. And Dyson taps fellow British astronomer Arthur Eddington to help organize the observational teams. Now, Eddington was himself an early and public champion of the general theory of relativity. In fact, during one of his own public lectures on the subject, an audience member commented,
Professor Eddington, you must be one of the 3 people in the world who understands Einstein's theory.
When Eddington didn't answer, the audience member encouraged him.
No need to be modest, Eddington.
On the contrary, I'm trying to think who the third person is.
Eddington and Dyson organized 2 teams to head out to locations that will experience a total solar eclipse. The city of Sobral near the Amazon jungle and Principe off the west coast of Africa. The challenge was weather. On the morning of the eclipse in Principe 100 years ago today, the rains were torrential. And as the 2:13 p.m. eclipse approached, the sun toyed with the astronomers, poking through the clouds, winking away, reappearing. Finally, with just a couple minutes to go, the cloud cover cleared, and the astronomers took as many photographic plates as they could. The weather in Sobral was somewhat better, but that team suffered from its own challenges, largely to do with technical issues with the equipment, so their data was also far from pristine. So the final result would require a careful blending of all the observations, analysis that would take a couple of months. Einstein waited patiently for the results.
If my theory of relativity is proven successful, Germany will claim me as a German. The Swiss will call me Swiss, and France will declare that I am a citizen of the world. Should my theory prove untrue, France will say I'm Swiss, the Swiss will say I am German, and Germany will declare I am a Jew.
Finally, on September 22nd, 1919, Einstein receives a telegram summarizing the results of the expeditions, and he does what any good Jewish son would.
Dear Mother, today a joyful notice. H.A. Lawrence has telegraphed me that the English expeditions have really proven the deflection of light at the sun.
It was astonishing. Einstein's wild ideas about warps and curves in space and time, it wasn't pie in the sky. It was real. Einstein had used complex math to fashion a new understanding of gravity, and the universe somehow knows about the math and obeys the equations. During all the well-deserved congratulations, a student asked Einstein what he would have said had the observations not confirmed his prediction.
I would be sorry for our dear Lord, for the theory is correct.
The official public announcement took place in November 1919 at a meeting of the Royal Society in London.
The results of the expeditions to Sobral and Principe leave little doubt that a deflection of light takes place in the neighborhood of the sun, and that it is of the amount demanded by Einstein's generalized theory of relativity.
The Times of London, the New York Times, just about every other newspaper in the world picked up the story. And with the media frenzy, there was an intense public interest to learn about relativity, which catapulted Einstein virtually overnight into a revered figure worldwide. It was an enormous triumph for science, for human ingenuity, for Einstein. Einstein, the public figure, he knew this well. But for Einstein, the scientist, this was merely a step, albeit an important one, toward the ultimate goal.